Okay, we will continue our topic on matrix inverse. Okay. Matrix inverse. Okay, matrix inverse. What's the definition of matrix inverse? The matrix inverse we can write as A. This is a 2D matrix, A to the minus 1. This is defined as A negative 1A will be equals to A negative 1 equals identity matrix, equals the identity matrix. And you can see that identity matrix is a square matrix. This A and A dash 1 has to share the same dimension. So it has to be a square matrix for an inverse matrix. So it's a square matrix multiply by its inverse gives identity matrix. Okay. So this is the definition of the inverse matrix. What is the motivation why we need to learn matrix inverse? Okay, the motivation of inverse matrix. So it will be used for solving, for example, linear algebra equations AX equals to B. The inverse matrix will be important. If you have linear algebra equations AX equals to B, then in order to solve the solution of X, then what we can do is we can times A inverse to both sides. So A inverse AX equals to A inverse B, right? And you know that A inverse A, based on the definition, will be the identity matrix. So it will be IX equals to A inverse B. And there is definition for the identity matrix. So note the identity matrix operating or operation on a matrix or vector won't change its original quantity. Okay, so what this note means that when you have an identity matrix operates on a vector, for example, X, it won't change the original quantity of X. So Ix will be equals to X. Then thus our previous equation will be X equals to A inverse B. She's a 1D vector. So the inverse matrix can be used to solve the solution of X for linear algebra equations. That is one of the motivation for inverse matrix. Then how we get the inverse matrix from a matrix A. So how to get A inverse if A is known. There are several ways to solve. For lower dimension, for example, the things can be solvable, the lower dimension. We can use the first method is A inverse will be equals to C transpose divided by the determinant of A. Okay, so this C is the cofactor matrix. Okay, the cofactor matrix of A. We will make an example how you get the cofactor matrix. The second method is called Gauss-Jordan elimination. Okay. Then for higher dimension, for things hard to solve, then we will use numerical method. Such as LU method and so on and so forth. We will talk about later how we use numerical method to solve inverse matrix. So for today's purpose, we will solve for the simple one. For the lower dimension, we will use an example and solve using method 1 and method 2 to get inverse matrix of A. Okay, and let's make an example. For example, let's make a simple 2 by 2 matrix of A, 4, 2, 3, 1. And remember, this has to be a square matrix in order to get the matrix inverse. If that is not a square matrix, it's not n by n, then we couldn't get the matrix of inverse, okay? So it's a square matrix, meaning that dimension has to be n by n, okay? Let's use method 1 to solve the matrix inverse. So method 1. We have method 1 is A inverse will be equals to C transpose divided by the determinant of A, okay? And let's first solve what is the determinant of A. It's very simple. It's 4 times 1 minus 2 times 3, that is minus 2, okay? And the C is the cofactor matrix of A, okay? And the Cij, so the element inside this cofactor matrix, will be equals to minus 1 to the I plus j power times Mij. This Mij is basically deleting the row of I, the column of j of the A matrix to get this new matrix M, okay? So for the cofactor, let's solve one by one. So there are C11, C12, C21, C22 for this cofactor matrix. The C11 will be equals to minus 1. The power of I plus j will be 1 plus 1, so 2. Mij, so M11. And M11 is basically deleting the first row of A, deleting the first column of A, and the left part, so which is 1 here, okay? So it's minus 1 squared times 1 equals 1. C12 is minus 1 to the I plus j, which is 1 plus 2, so it's third order, M12. And that will be minus 1 times M12 is what? Deleting the first row of A and the second column of A. So left is 3 here, equals minus 3. C21 will be minus 1 to the third M21, and that will be deleting the second row of A. The first column of A, that will be 2. So it's minus 1 times 2 equals minus 2. C22 will be minus 1 to the 2 plus 2 will be fourth order, M22. And M22 basically is deleting the second row and the second column. So left this A11 here. That will be 1 times 4 equals to 4. Okay, so to what is our cofactor matrix? Is all this element together. So the cofactor matrix will be 1, -3, -2, and 4 here. And in order to get the inverse matrix of A, you need to do the transpose of C. So the C transpose will be 1, -3, -2, 4. Okay. And you already know what is the determinant, which is -2 here. So in the end, the A inverse will be the transpose of C, which is 1, -3, -2, 4, times the 1 over determinant, which is 1 over -2. So in the end, the A inverse will be equals to -half 1, 3 over 2, -2. So this is the A inverse using the first method, which is the transpose of the cofactor matrix of A divided by the determinant of A. Then the second method, we will use Gauss-Jordan elimination to solve the A inverse. And let's see how we use Gauss-Jordan's method. Okay, we will use the same example here. So method 2. Gauss-Jordan elimination. This is very simple, similar as compared to the Gaussian elimination. The Gaussian elimination is using row operators, row elementary operators to apply to the argument matrix to make it as an upper triangular matrix. Then you use the substitution to get the final solution of X, right? For Gauss-Jordan elimination is also apply row operations, row elementary operations to transform the argument matrix basically to an identity matrix as follows. So you have the argument matrix, which is AI. So this is A, which is a 3 by 3 matrix. You have identity 1 0 0 0 1 0 0 0 1, and you will transpose to identity matrix 1 0 0 0 1 0 0 0 1 with U matrix inverse. Okay, so this is Gauss-Jordan. We can think about this method. We can think regarding this method. You have AX equals to I. AX equals to I, and based on the definition of matrix inverse, this X has to be A inverse, A inverse. And in order to solve this X, what you can do is to solve X, you need to solve the argument matrix AI to get IX. So that is how we can translate the argument matrix into an identity and get U matrix inverse, which X is U matrix inverse. Okay, and let's use the same example as the method 1, but using different method, Gauss-Jordan elimination. Okay, so for example, we have a 2D matrix. A is equals to 4 3 2 1. And we are trying to use Gauss-Jordan elimination to get this A inverse. To get A inverse. First, we need to build this argument matrix, which is A, I, right? So that is 4, 3, 2, 1, 0, 1, 0, 0, 1. That is the argument matrix. And then we need to apply row operations to make this matrix look like 1, 0, 0, 1 with x, 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 x here. So we will use row matrix. The first row matrix will be the second row. The newly updated second row will be the second row, the current second row minus 3 over 4 R1. So in order to make this 3 to be 0, we need to minus 3 over 4 times the first row. Then the first row is now changing. It's 4, 2, 1, 0. The second row, the first number will be 0. The second number will be 1 minus 3 over 4 times 2, which is minus half. This one will be minus 4 over 3, and that one will be 1. Okay. Then the second row operation, what we will do is trying to make this number to be 0. So the first row will be equals to, the updated first row will be equals to the current first row plus 4 times the second row, okay? So in order to make this 2 to be 0, then what we can get will be 4 plus 0 times 4 will be still 4. The second row is now changing, so we can write the second row first. Then this number is 2 plus 4 times negative half will be 0. This one will be negative half, negative 2, and this one will be 4. Okay. Then we need to make this part to be identity matrix. So the first row, the newly updated will be the current one divided by 4. The second row will be the second row times negative 2. We can do together or you can do separate. It doesn't matter because you are now applying one to the other. So it's just a changing itself. It will be 1, 0, negative half 1. This one will be 1, 0, 1, 3 over 2, and negative 2. And you can see that the A inverse will be this part. So the A inverse will be negative half 1, 3 over 2, negative 2. Okay. And this one is the same result as what we get from the previous method. That's C transpose divided by the determinant of A. So they are the same. And for Gauss-Jordan elimination and the method one, the cofactor matrix, we usually apply to a lower matrices where the new analytical solution can still apply. But if you go higher dimension, for example, N is super large, then it's almost impossible to use such method to get you inverse matrix. Then that time we need to apply for numerical solutions, okay? And there are some properties of the inverse matrix, some properties. Or you can say some convenient relationship for the inverse matrix. So the inverse matrix, convenient relationships. The first one, if my A is a diagonal matrix, basically only diagonal has the number. You can directly get you A inverse will be AII to the power of -1. So all the diagonal inverse value will be the inverse matrix. You don't need to apply either the method 1 or method 2 or numeric method. That is directly output. Easy one. Then also there is some rule for the inverse matrix. If you are trying to get AB, product of the inverse will be B inverse, A inverse. Okay. And we can prove this multiplication to prove that, to prove this one, we can set AB inverse that is equals to C. And based on the definition of the matrix inverse, we know that AB times AB inverse. So matrix times its own inverse will be is equals to the identity matrix. So we can say A, B, C will be an identity matrix. Okay. And then you also know that if you can write in this way, A, B, okay, times B inverse, then this part will be identity matrix. Then identity matrix times A will be A itself. If you times another A negative, this will be identity matrix again. So this thing will be equals to identity matrix as well, okay? Then what you can get is, this is identity matrix. This is, so equation 1 is identity matrix, equation 2 is identity matrix. Then what you can say is that AB, C will be equals to AB, B inverse, A inverse, okay? And this part is the same, so that the C will be equals to B inverse, A inverse, and you know C is AB inverse, right? So AB inverse will be equals to B inverse, A inverse. Okay, so we can prove such multiplication product for AB inverse. Okay.